Hello, I'm Giacomo Rizzieri and I recently obtained my PhD in structural, seismic and geotechnical engineering. During the past 3 years, I worked under the supervision of Professor Massimiliano Cremonesi and Professor Liberato Ferrara. My work lied at the intersection between computational mechanics and material modeling, and I've been working with both the research groups with the aim to develop new computational tools for simulate 3D printing with advanced materials. Before entering in details with my research, let me take a step back and explain to you what is 3D concrete printing. This is a very new technology which is used to optimize the construction process by extruding a cementitious mortar through a fully automatized nozzle in order to create complex structure and objects. However, it is clear that this technology is very complex. For these reasons, it's necessary to develop adequate numerical and regulation tools to control it and optimize it. In my research, I started from an already developed computational tool for fluid dynamics and I tried to extend it to simulate 3D concrete printing. The first step is to adapt it to deal also with more complex type of materials. In the case of fresh concrete, the behavior is dictated by the state of stress. For lower state of stress, the material behaves like a solid, while if it is subjected to vibrations, it will start to flow like a fluid. Mathematically, this type of approach can be reproduced with the Bingham model. However, this is not the most accurate choice. In fact, the Bingham model is neglecting elasticity. For this reason, during my PhD, I tried to implement and develop also viscoelastic and elasto-viscoplastic materials. Additionally, I enhanced them, adding also the time dependency in order to take care of the fact that the material properties are actually evolving in time due to the hydration reaction of fresh concrete. In parallel, I started implementing a computational framework to represent the process of 3D printing from the numerical point of view. This involves applying complex boundary conditions, for example, to represent contact of the layer with the base plane or contact of multiple layers, one on top of the other. All this framework has been implemented in a Fortran environment and, combined with the material models I described before, is able to reproduce in a very accurate way the 3D printing process. I validated the framework by reproducing the printing scenarios obtained by experimental data and comparing cross-sections, obtaining very good results, and thus I decided that my model could be applied to more challenging applications. The two main results that I want to focus on here are the fact that we were able, by conducting a lot of simulation on single-layer filament printing, the generation of a map describing all the possible types of flow regimes during 3D printing and correlating them also to the possible cross-sections. Secondly, I tried to validate the framework also for multiple layers prints involving complex geometries such as real 3D printed walls or complex parametric objects. Also in this case, I was able to compare results with experimental data from a collaboration with TU Eindhoven, and we compared the cross-sections but also the failure rates. Basically, we compared after how many layers the object that we were printing were supposed to collapse.